Let's move on with building our own AI applications. So let's now take our knowledge of AI and large language models even further. And as I've said, start building our own apps. So this is where large language model frameworks come into play, because these frameworks, they just simplify and sort of streamline the process of working with language models, because they provide tools and interfaces which make it easier for us to integrate models into applications or simply manage prompts or handle context and parse outputs. For example, model interfaces allow us to connect to virtually any large language model API like OpenAI or Anthropic, or even run open source local models like Ollama without worrying about the underlying complexities or dependencies of the model connection. Then with prompt management capabilities, these help us to create, store, and maybe version prompts, which ensures that we have consistent or which ensure consistency, and they pretty much make it easier to refine our interactions with the model itself. Now, context handling is also very important for managing the conversation history or the relevant context, especially in applications like chatbots or, for example, multi-step workflows. And then we have output parsing, which provides utilities to extract structured data from the model's responses, which is often necessary for real-world applications. And there are some popular frameworks like LangChain, Llama Index, or Hugging Face transformers, for example. And in our workshop today, we will primarily focus on LangChain. Now, using application frameworks for sort of building any AI solution is very cool, because they, again, simplify and streamline this entire development process. Because first, they help us reduce boilerplate code, because they can handle repetitive tasks like API calls, error handling, or even data processing. So we can focus on the core logic of our application instead of reinventing the wheel. And they also just simplify development itself by providing some abstracted tools and interfaces for common tasks, which makes it easier for us to simply experiment, iterate, or build applications quickly without worrying about all of that low-level implementations, yada, yada. And another big advantage is the improved maintainability, because these frameworks offer a structured approach to things like prompt engineering or application architecture, which makes our code base easier to manage and maybe even scale over time. And they also enable us to create more advanced workflows. For example, we have a built-in support for techniques like few-shot learning, retrieval-augmented generation, or we can just chain multiple large language model interactions together, which we would otherwise have to customly code. And finally, these frameworks are exceptionally good at ecosystem integration, because they can just connect seamlessly with any database, vector store, and other tools in the AI ecosystem, which makes it easier to build end-to-end solutions. So in short, these frameworks simply save time, they reduce complexity, and unlock sort of advanced capabilities, which makes them a very cool tool for anyone building AI application. Now, as I've just mentioned, we'll focus on LangChain, which is one of the most popular frameworks for building AI applications right now. It's an open source framework which is designed to simplify working with large language models. And what makes it stand out is its ability to handle agentic task workflows, meaning it can autonomously perform tasks by simply chaining multiple large language model interactions together. So this framework is very powerful for creating applications that would require complex workflows such as combining retrieval-augmented generation and multi-step reasoning, or maybe integrating external tools or APIs. So let's dive deeper into what this LangChain can do and how it helps us to build smarter, more efficient AI applications. So let's take a closer look at these key components of LangChain, which work together to build a very cool AI application. First of all, we have document loaders, which are used to load and process the data from any, data sources such as PDFs, websites, or even databases. So they prepare the raw data for use in our application. Now, the vector stores, they store numerical representations of the text from the document, which are called the embeddings, which allow for a very efficient similarity search for our model. And they're very important for tasks like retrieval-augmented generation, where the model needs to find relevant information quickly. Now, the prompts are the instructions or the queries we give to the language model. And LangChain helps us to manage and structure these prompts to ensure that the model generates accurate and relevant responses. Of course, we have the models themselves, which are, models like GPT-4 or Llama. And LangChain simply provides integration with all of these models, whether they are cloud-based or running locally. Chains, they allow you to link multiple large language model interactions together to perform certain complex workflows. For example, we can combine the retrieval and the summarization workflow, or maybe even an entire question answering into a single process. And agents, on the other hand, they take things a step further by enabling autonomous task completion. They can make decisions on their own, interact with tools, and they can adapt their behavior based on the task at hand. So together, all of these components make LangChain a very interesting and flexible framework for building AI applications, which are efficient, scalable, and capable of handling complex tasks. Now, throughout this next demo, I would like to show you some examples of how we can build simple but effective AI applications of LangChain. So I've prepared a few examples to show you how LangChain can be used to build our apps. And I will start by setting up just a basic chatting application, and then we'll move on to something more advanced like loading web content, and we'll finally also add a UI for another type of content loader. All right. But before switching, let me give you a quick overview of the languages and tools I will be using in this demo. Of course, I will be working with Python, which is a popular programming language for AI development because of its simplicity and versatility. And of course, we will be using the big LangChain library, which provides us a range of tools and utilities for working with our models. And additionally, I'll be using either Ollama or the OpenAI models to interact with the models and generate responses. And I would like to begin to showcase Ollama, and later we will switch to OpenAI because of the hardware limitations on my machine. All right, as promised now, let's start with the first example, which is just about setting up the large language model and LangChain for our AI application. I promised you we will start off easy, so I will just demonstrate two easy programs which I've built. So this first one is pretty straightforward. So just so you can see that we can build an AI application with effectively only 2 lines of code. Of course, we need to import some libraries or some tools from this massive LangChain library, like the Ollama to handle our Ollama models. And I also imported a callback manager. Now, a callback is some sort of a little helper that handles what happens when the model generates a response. Now, I also imported the streaming standard out callback handler, which is just a specific callback, which prints the model's response to the screen as it generates. So it's kind of like a stream event. So don't worry, we will see alternatives to print out our responses later. And yeah, so with this line, I simply create a model object or an instance which we can interact with. And we state that we want to use the Ollama Llama 2 model and how we would like our response to look like with our callback manager. And in the last line, I simply tell the model what to do. Basically, we send the model a question about, yeah, the Roman history. And if we give it a go, I mean, it does run locally, so I do have to be patient. I think I've run into a little problem here. So another service is going here, which is great. Yep, let's try it again. Yes, it's doing something. Yeah, and it's thinking very slowly, but it thinks. Perfect. This is just what I wanted. Some interesting facts about the Roman history. Okay, I think I will just interrupt this so we can move on to another example. So let's do something more interesting. So what if I want to have a chat with my large language model through my application? So let's look at this example here. Don't worry about the API keys you see in the commented out section. I only add this so you can have a sneak peek what will happen in the later examples as we will switch to the ChatGPT models. So we see that we need some more libraries here, but we will get to that. First of all, we simply create our model again. And this time I don't need the callback handler because I'll simply print out the output manually. So we set up the model and I then create a memory system so the chatbot can remember what we said during our conversation. I then create my very first chain, and in this case, I use a conversation chain, which simply combines my model and the memory system all into a chatbot. And with verbose, I simply say that the chatbot should print out extra info about how it works. And then we already enter the main chat loop right here, saying that as long as the program runs, I want to read the input I give the system. And with this response object, I start the chain and send the query to the chatbot, which is then generating and printing the whole response. Now, the only downside here is that I only print the answer as a whole, meaning that I don't really see the generation word by word. So with my Mac, I think we have to wait some seconds. So I'll just say hello, something very short. Yeah, and we can already see that the program is printing out the entire response object so we can see this entire chat. Okay. it didn't just say hello, it did a little bit more, but that's perfect. And as you can see, I can simply, write on and have a conversation with the model. We just stepped through our basic models. That is what we just discussed. We simply load our model. We created our very first chain and had a little chat with our model. So for my next trick, I want to use RAG, Retrieval-Augmented Generation processes to enhance the responses of my AI application. But before we head into this, let's maybe take a deeper dive into how this RAG process actually works. So I already told you a bit about the LLM and RAG process, but this time I want to show you a bit more about the general process. So with this diagram, I simply tried to visualize the retrieval-augmented process of an LLM generation. So first of all, the user provides a simple query to the system, which is the starting point. Then this query is passed through what's called an embedding model, which converts the information into numerical vectors, which the model can work with. This is used to later find similar or relevant information in the database, which is the next step, because the vector database stores the pre-computed vector embeddings of documents or any other knowledge source. And the query vector will then be compared to these vectors. And it will retrieve the most relevant contexts or chunks. These retrieved contexts can then be ranked based on their relevance to the query, and the top results are then passed to the large language model for the final generation. Now, when it comes to different sources we can use for retrieval, you can see that we have a few options in LangChain. We can load specific files like JSONs, CSVs, PDFs, or even an entire directory. We could also load web content, which we will see in a bit, from URLs or pandas data frames. Or we could simply connect to cloud providers like Azure, AWS, or even connecting to applications like Slack or Figma. And I think by now there are over 160 different loaders available for LangChain, so I think that should be enough. And most of the time, we only need a correct API key to actually use them. Now, loading the specific content is one thing, but we can't just throw an entire document or content at the model because it just won't be able to process it effectively. I mean, imagine if we have a large PDF with over 100 pages. So if we were to ask something specific from its content, it would be far more efficient if we just provide the relevant parts of the document to the model. So we need to break down the content into smaller, more manageable pieces. I think we've heard that before. So this process is called chunking or splitting. It helps the model improve the relevance and the context of preservation of the retrieved information. So when chunking, it's important to also consider an overlap between the chunks to ensure consistency by sort of allowing a shared context at the end of one chunk and at the beginning of the next. Next up, we have to convert this text into numerical vectors that the model can understand. This is where the embedding models come into play, which are used to convert the text into numerical representations. This means that the model can understand the relationships between words and phrases and allows it to find similar or relevant information in the database. And there are various embedding models available, such as BERT, Word2Vec, or even Ollama's and OpenAI's own embedding models. The vector database is then where this pre-computed vector embeddings of the documents or any knowledge sources are stored. It's an optimized storage for similarity search in high-dimensional spaces, which is important for finding relevant information quickly. So to improve performance, we can use optimization techniques like quantization or indexing, batch processing, all for efficient generation of responses. In this picture, you can see a simple illustration of how the vector database actually works. So we have a query with a cat. This query is converted into a vector representation, and it is compared to the stored vectors in the database. Each data point in this database is also represented as a vector, and the query vector is then compared to these vectors to find the most similar or relevant information. So in this case, the pink region highlights a cluster of similar cats, which are semantically close to the query, and the system retrieves the most relevant information based on this very comparison. Now, there are also two more advanced techniques for retrieval-augmented generation, which I just want to mention very briefly. Like we heard before, we can re-rank the chunked context of a chunked document. And re-ranking is the technique that we can use to refine the initial search results and improve the relevance, which is done by using either more complex models or algorithms to rank these retrieved information. And another technique is to represent the information as a graph. That means we can capture even relationships between the entities in the retrieved information and represent them as a graph structure, which helps the model to sort of navigate the graph to find relevant information based on the relationships between entities. All right, I think we've heard enough now again, so let's finally move on to building our RAG application. We can see that there's a lot more going on here, but don't worry. So as we are now using OpenAI models the very first time now, oh wait, sorry, it's too long. That's more like it. And exactly. As we're using OpenAI models this very first time now, I somehow need to provide some credentials to connect to the platform's model. In my case, I stored my API key in an environment file, so I simply use the .env library to read this file and find the key. Then you'll notice I have two functions here. In this very first one, I create a vector store from the content of a web page. So we have to define a loader first, which in our case should be simply for the website. This loader retrieves the web content at a given URL. Then we simply split this document into smaller chunks with, in this case, no overlap, for example. And then with OpenAI's own embedding model, we simply create the text chunks into numerical embeddings. And at the end, I create a searchable vector database from the text chunks and their embeddings. And in this example, I am simply using the Chroma database, which is a simple storage for this info in my max memory. Now then, this next function summarizes the content of my web page. So first of all, I create the vector store by calling the first function, and I then simply initialize my model. Then I can create a prompt template for the model to perform exactly how I want it to. And you can see this little text placeholder, which will be later filled with the information from our finished RAG process. And afterwards, I simply create a chain to combine the model and the prompt for processing text. And with my vector store, which I've defined earlier, I search for the three most relevant text chunks and simply summarize them. So for each chunk, GPT 3.5 in our case will create a summary, which is stored in a list. And at the end, I simply return this joint summary. So if we run this again, we'll have to wait a few seconds. And then I can enter any URL I want. So let's take, for example, yeah, why not take Infralovers? So then it creates the embeddings, it searches for content, and in a second, we should have a summary of our results. It runs to chain, and there we have it. Infralovers offers custom IT trainings for high-performance teams. That's just what I wanted. Perfect. That's just what we've talked about. I have to load the API key as I'm using OpenAI. I also have to create the vector store to save the actual content. And then I use my large language model and create a chain to actually get a summarization of the content which I've received. And now for the final part of this demo, I want to have the ability to chat with the model about my very own document content, and all of that, if possible, wrapped in a nice, simple user face, which is because I want to introduce Streamlit, which is an open source web application framework for simply building machine learning and data science apps quickly and efficiently. Yeah, Streamlit basically provides a simple Pythonic API, which allows us to create interactive web applications with basically zero effort. And it supports real-time interactions, so we can see changes instantly when we modify the code. It also offers a range of features like Markdown, widgets, and even more, making it very easy for us to build user-friendly interface. Now, this time, instead of working with a web page, we're now working with a PDF. And the goal is to simply upload a PDF, process its content, and then chat with it using OpenAI's GPT 3.5 model. So as we're using the OpenAI model again, I need to get my API key again. So yeah, then you'll notice that I have, again, two main functions. We have in the first one, I simply process the content of my PDF file, and I simply create a vector store from it. So first of all, I have to save this uploaded PDF as a temporary file. And then I use a PDF loader to extract the text from the file. And since the text might be too large to process all at once, I again have to split it in smaller chunks. After that, I simply use OpenAI's embedding model to convert these text chunks into numerical embeddings. And at the end, I create a searchable vector database from the text chunks and their embeddings. I'm also using the ChromaDB again, so all in all, it's the same as we saw before. Now, in this second function, I set up a conversion chain to chat with my actual PDF. So first of all, I initialize the OpenAI model with a low temperature to make the responses more focused. I then add a memory system to the store. So basically, so I can store the conversation history again. And finally, I simply combine the model, the memory, and the vector store in a conversational retrieval chain. And this chain then allows for the chatbot to really retrieve the most relevant chunks of text from my PDF and use them to answer the questions. Now at the end, I handle the user input by passing all of their questions to the conversation chain. The chain retrieves this relevant text from the vector store, generates a response using the OpenAI model, and it updates the conversation history. And at the end, the app then just displays the full chat history, which is basically alternating between the user's question and the AI's responses. So when you run this app, you can upload a PDF, ask questions about it, and have a back and forth conversation by the AI with the AI about the document. Also, you may have noticed some minor additional code for Streamlit with ST here. For example, I use the Streamlit session state to store the conversation chain and the chat history, so the app can keep track of the interaction, even as the user continues to ask questions. Now, there's also a file uploader for uploading a PDF, a little spinner to show a loading animation while the PDF is being processed, and of course, a text input box for typing question. Now, this Streamlit features make the app very interactive and easy to use. So if I simply run this now, I can see that Streamlit is building this application for me. And I can simply tell Streamlit to run this very app right now, which I think you can see right now. So I will just share my whole screen. And we can see when it's uploaded, it's already processing it and loading all the PDF content. And if I were to ask a question about this PDF now, like this document about, we hopefully get a meaningful answer. Yes, this document provides guidance of and examples of crafting haikus, a traditional form of Japanese poetry, which is perfect. Let's assume we've now just built our AI application. Now the question is, how can we ensure that it is really working as expected? Now this is where testing comes into play, because we know testing helps us to make sure that our applications are reliable and give accurate results as we know it. So by checking how our models perform, we can spot any mistakes or problems early on, which is important when we update our models or add new features, as it helps to keep everything run smoothly. We also need to confirm that the answers we get from the model match what we expect. This way, we can ensure that our application meets our needs and the needs of the people who will use it. And for this, I would like to show you a few examples of how we can test our large language model applications. So one way we could ensure the quality of our large language model applications is by building something that's called evaluations, which are tailored to our specific use cases. And this typically involves defining evaluation metrics, which would align with the goals of our application and create benchmarks to assess this model's performance. For example, we can define test cases with clear inputs and expected outputs, as shown in the code snippet here. So by running these test cases, we can compare the model's actual output to the expected results and determine whether it meets our standards. So in general, this process helps us to identify areas where the model might need improvement, and it ensures that it consistently delivers accurate and reliable results. So evaluations like these are essential for maintaining the quality of our applications. And we could go ahead and spin this even further and simply use an LLM itself as a judge for automatic evaluation prompts. Now, this approach is useful when we're dealing with some sort of subjective or very large or complex outputs, where the exact evaluation methods might fall short. So by using the large language model to assess its own or another model's responses, we can perform pretty much any large-scale testing. For example, the large language model can compare generated outputs to expected results, rate their quality, or even provide feedback on areas for improvement. And this method is especially valuable for tasks like, for example, creative writing, summarization, or nuanced question answering, where the correct answer might not always be a clear cut. So using the LLM as a sort of judge allows us to scale evaluations, but also we can maintain a focus on the quality and relevance. So let me show you an example of how we can use this language model as a judge to evaluate its own or another model's outputs. So in this case, we start by defining a prompt for generating a short story based on a specific theme, such as in this case, an adventure in a mythical forest, for example. And the language model generates this story using exactly this prompt. Now we define a second prompt for evaluation. Here the LLM should act as the judge, rating the story on creativity, coherence, or maybe grammar. And it should provide a brief explanation for each rating. And this evaluation is then performed automatically by another instance of my language model. And then there's also the process of prompt refactoring, which is simply an iterative approach to improving the quality of prompts for simply better results. And this involves kind of analyzing the outputs which are generated by the model, identifying areas where the prompt could be clearer or more specific, and refining it to achieve the desired outcome would be cool. And this is also where prompt engineering plays its role. So let me walk you through another example. Here, we can start with a simple user input, such as explain the impact of the Industrial Revolution. And in this first step, we use a large language model to enhance this input by generating a more detailed, more comprehensive, more coherent prompt. And the enhancement process then adds specific details, context, relevant questions to ensure that the model provides a thorough response. And in the second step, the enhanced prompt is then passed to another language model to perform the actual task we gave it in the beginning. So this refined prompt helps the model to generate a more accurate, maybe a more detailed output. And by chaining these steps together, we can again improve the quality of the outputs. Now the cool thing is, we can stay in the LangChain ecosystem and simply use LangSmith to test and manage our large language model application. And as you might think, as LangSmith is very deeply integrated into the LangChain ecosystem, it also provides some powerful tools and features to help us manage the entire lifecycle of our large language model applications with tracing, evaluations, testing, monitoring, and versioning of our models and their behavior. So let's start with tracing in LangSmith. This feature allows us to visualize the execution of language model change, which makes it easier for us to debug and optimize our applications. For example, we can identify bottlenecks, errors, or inefficiencies within the chain. It also provides insights into token usage and latency. It helps us to understand how resources are being consumed. And in the code example here, we use the LangSmith callback handler to trace the execution of a simple chain, which generates a simple joke about programming. And by enabling the tracing, we can monitor the chain's performance and identify areas for, potential improvement. Now next, LangSmith features datasets and testing, which means that LangSmith allows us to create datasets for consistent evaluations of our large language model applications, which is very useful for running automated tests to ensure that our chains perform reliable in any different scenarios. So in this example here, we create a dataset called programming jokes. And we add an example input and an example output. Then we run the tests on this dataset using our chain and evaluate the results based on specific criteria, such as humor, for example. And this process can help us to compare the performance across different model versions, for example, and it ensures that our application meets our standards. And finally, we have monitoring and versioning, because LangSmith provides tools to also track production performance metrics such as the latency, the accuracy, or even user interaction, which can help us to monitor how our application performs in real-world scenarios. And additionally, LangSmith also supports the versioning, which lets us manage pretty much different versions of prompts, chains, and even models, which is very useful for, let's say, A and B testing, where we can compare the performance of different versions to determine which one works better for us. And with all of these features, I think LangSmith can help us that our applications remain reliable and adaptable over time. Okay, that would be it for the whole application building and testing part.